This video is going to discuss the period of time for a planet to go around the Sun, called the sidereal period, measured with respect to the stars. So if we have at midnight the same star on our meridian looking towards the south from one year to the next, talking about the Earth, then that is the year for the planet to go once around in its orbit with respect to the position of the stars. There's also the synodic period. The synodic period is the length of time until a planet gets back into the same configuration with another planet and the Sun. So we're going to take the point of view of being on the Earth and take a look at the synodic periods of Venus and Mars and Jupiter and so forth. Just some background to be able to do this approximation of the synodic period and then the calculation of the synodic period. So it'll be helpful to take a little look here at an image of the solar system. Got this off of Wikimedia Commons, posted by Laos Loss. On the left, we have the inner solar system. So the Sun, Mercury takes 0.24 years for one orbit, the sidereal period. Mars, 0.62. Earth, of course, 1 year. Mars, 1.88 years. And then, so that's Mercury, Venus, Earth, and Mars. I'm going to ignore this asteroid. And then the outer solar system, Mars is too small to really label here, but Jupiter, 11.9 years to go around the Sun, Saturn, 29.4 years, Uranus, 84 years, and Neptune, 164 years. Do you see a trend in the sidereal period for the planets as we get further away from the Sun? And, of course, your answer is yes, 0.24, 0.62, 1, 1.8, 11.9, 29.4, 84, 164. The planets that are more distant from the Sun take more time to complete their orbit. Their sidereal period is larger. And, if we would line up all the planets in a straight line and then start the race, so to speak, of course, Mercury is going to win in terms of if the race is completing one lap of the solar system. Mercury only takes 0.24 years to get back to the starting line. Venus will come in second. It'll take 0.62 years to get back. Earth is third, and so on. As we're observing the solar system, we're on a moving platform, and that complicates our view of the positions of the planets as the months and years go along. So that's where the synodic period can help us to understand when will a certain planet be back in the same configuration between the Sun and that planet as viewed from the Earth. So we're going to be looking at the synodic period. So I'm first going to do this, and the Earth is going to be lapped by Venus, by Mercury, and when we're on the Earth, we're going to go around in a shorter amount of time than Mars, and we would perhaps want to know how long is it till we get back to the same configuration. We're talking about wanting to know the synodic period. So here's a sketch here and some equations. I'm not going to use the equations first. I'm going to do the rough approximation of what happens here first. But if P is the sidereal period, length of time to go around the orbit using the stars as our start and finish line, we call that P. S is the synodic period, and if I just talk about here for Earth and Venus, I have this set up with inferior conjunction, where Venus is in between the Sun and the Earth on a straight line here. And we're asking, when is it again that we'll have Earth and Venus in a straight line? Might be over here or be over here, but Venus and Earth lined up together with the Sun on a straight line. That would be the synodic period. We do not have to get back to this configuration I've drawn on my page here, where Earth and Venus are exactly where these first dots are. We're just looking for the length of time, the synodic period, when we have Sun, Venus, and Earth in a straight line. Well, let's just do this calculation, I'm going to work with days instead of years. So for Venus, it takes 225 days to move around the sun. Of course, the Earth 365.25, but I'm just going to use 365. This graphical work is approximate anyway. So 365 days for our sidereal period. So let's let Venus go around once in its orbit. So here's where Venus starts, and I'm also going to let that dot be where Venus is after 225 years. Where's the Earth after 225 days? Where is the Earth after 225 days? Well, to locate that position, I could do 225 divided by 365. That will tell me the fraction of the orbit that we've gone through. And when you do that, you find that this is 0.62. So we've gone through 62% of the orbit, so over here someplace. And if I would convert this to degrees, if I just multiply by 360 degrees, one full orbit, I find that I get roughly 222 degrees. 222 degrees. Well, down here is 180. Over here is 270. Over here would be 90 degrees and 0 degrees at the top. So I've moved around in orbit, past 180, but not to 270. So I'm just going to approximate this. If I subtract 180 from here, I'd have 42 degrees. So not quite the middle, but just right about here. This is all approximate. So I'm going to label that where the Earth is after 225 days. Venus has gone around to here. The Earth has gone around to here. Has it ever occurred during these first 225 days that we have Sun, Venus, and Earth in a straight line? For example, over here. If Venus is here, the Earth isn't going as fast, so it's back here. So that's obviously not a straight line. You can work out others on your own. I'm not going to clutter up this diagram. No, the Sun, Venus, and Earth have not formed a straight line in the first 225 days. Let's go another 225 days. So I'm going to let Venus be back at this starting point again, V3. Where is the Earth after the next 225 days? Well, another 225 days. I'm going to do the work over here. Plus 225 days. We're now at 450 days. And the Earth is going to be past this first point because 365 days is how much time that takes. So I'm going to subtract off 365. I'll move this up a little bit so you can see my calculations. If I subtract 365, I get 85. If I divide that by 365, I can find the fraction of this next orbit that the Earth has moved through, and I get 0.23. And if I convert that to degrees, I get about 84 degrees. So the Earth is sitting about here. And this is the third position. So Venus is to here, the Earth is here. Venus is getting closer to catching up with the Earth, but again, at no point in this route around here with the Earth has Venus been in a direct line between the Sun and the Earth. You can just do your own little jump, 10 days at a time if you wish, and you'll find that is the case. We've not had a repeat of the inferior conjunction. So we need to go a little further. And I can see that Venus is starting to catch up here. So this next time, I'm just going to advance. Instead of 450, I'm going to go half an orbit for Venus. So this is going to be my fourth position of Venus. And half an orbit, I would add half of the full orbit for Venus. So I'm going to add 112 to 450. So 450 plus 112, I get 562 days. And that's the position of Venus. Where is the Earth after 562 days? Well, I'll do the work over here. 562 minus 365 to account for the Earth going around one time. And someplace on my page I've worked that out. 562 minus 365 is 197 days. And then if I divide that by 365, I find that the Earth has completed, looking on my calculations here, the Earth has completed 0.54, 54% of an orbit, and that would be 194 degrees. And that makes sense. Roughly 180 days is half an orbit, and we're a little bit past half an orbit. So right about here, the Earth is still ahead. So let's go a little bit further, and I'm just in the realm of kind of guessing at places now, but I'm going to guess like 30 days farther. So where is the Earth and where is Venus after 592 days? After 592 days, again, I subtract 365. I get a number of days. I divide by 365. And you should check my work, but I got 0.62, which is 224 degrees. And just kind of by coincidence, I'm going to put an X here. So here's my Earth. My fifth position of Earth is that X. Where is Venus after 592 days? Well, Venus, 592 days. 450 days is 2 orbits of Venus. So if I subtract that, I get 142. If I divide that by 225, I come up with 0.63 and 227 degrees. So here we go. If I would take a line out to where the Earth is, Venus is a little bit past that. Venus is 227 degrees in its orbit. The Earth is 224 degrees. So we have gone past the time of, again, inferior conjunction, Sun, Venus, and Earth on a straight line. And I'm going to say roughly 590 days. I'm not going to bother to work it out, but roughly 590 days would be the time when we would have, again, in alignment, a situation where we have Sun, Venus, and Earth on a straight line. I don't know if I can put those circles in a straight line or not, but I'll do it this way. And as Professor Hartman from Midland University would teach me, if you just make the dots bigger, the line will pass through the dots. So there we go. We have inferior conjunction about 590 days. Now let's try some calculations and see if we're in agreement with what we've just worked out on paper. So I'm going to use the formula here. I'm going to use for the inner planet. The synodic period is the sidereal period, and then 1 minus p on the denominator. And for the case of Venus, I now need to work with years for the p, and I'll get a year number for the s as well. So converting the 225-day orbit of Venus roughly into years, I find that the value for the sidereal period is 0.615 years. So the sidereal period will be 0.615 over 1 minus 0.615. You should pull out your calculator and check the results of this calculation. But I come up with 1.6 years. And if I determine what the 0.6 is, if I just multiply here by 365 days, maybe 0.25, for 1 year, I come up with 584 days as a better version of the synodic period. So my guess was not quite right. I got 590 as a guess on my graphical work here, but the formula says 584 days. So in February 2017, Venus was very bright in the sky in the west after sunset. 584 days from middle February 2017, again, Venus can be found very bright in the sky on the in the west after sunset. That's the synodic period. That's when it's going to return to the same configuration. And going a little long here, so I'm going to, you could ask for greatest western elongation, greatest eastern elongation, whatever you have. The time between successive configurations as viewed from the Earth, Venus as viewed from the Earth, is going to be 584 days. If we do this for Mars, we have to use a different formula. For Mars, if we're interested in when does Mars get back to the same position in the sky, then we get S equals P over P minus 1. And you can see this would not work for Venus. The period of Venus is less than 1, so we'd end up with a negative result. And this formula would not work for Mars because the period of Mars is 1.88 years, and we'd have a negative in the denominator. We'd get a negative for the synodic period. We don't want that. We want what is the time in the future that we'll get back to the same configuration. So for Mars, we put in 1.88, and that's how I do 1.88, and here 1.88 minus 1, that's going to be 0.88. And use your calculator and you divide that out, and you get 2.136 years, or roughly 2 years and 50 days. That's the length of time between the reoccurrence of seeing Mars at a certain place in the sky. Not talking about being in the same constellation, but talking about, at sunset, Mars is in such a position with respect to the horizon, a certain angle away from the sun. It's going to take 2 years and 50 days, roughly 2 years and 2 months. If we do this calculation for Jupiter, the period of Jupiter is 11.9 years, roughly. So we'd have 11.9 minus 1 here. And you should work this out in your calculator. I came up with 1.09 years. That's 1 year and 34 days. If you do this for Saturn, we have 29.4 years for the period for Saturn. I'm going to let you plug that in. But for the synodic period, I came up with 1.035 years. That's 1 year and 13 days. And for Uranus, the sidereal period is 83.75 years. That's our p-value. Again, you should plug that in. I came up with a synodic period of 1.012 years. That's 1 year and 4 days. And then lastly, for Neptune, Neptune is 163.7 years for its period, and its synodic period is 1 year and 2.2 days. Do you see a trend in these synodic periods for the outer planets? 2 years, 50 days, 1 year, 34 days, 1 year, 13 days, 1 year, 4 days, 1 year, and 2.2 days. You should notice that the time is going down, and the reason for that is that for these outer planets moving very slowly, the Earth goes around in 1 year. Neptune has not moved very far at all in 1 year. 164 years for one orbit, roughly 2 degrees per year, very roughly 2 degrees per year. So if Neptune is here and the Earth is here, they're in a conjunction arrangement, or opposition, I should say, and Neptune opposite to the Sun, then we would have only a slight motion of Neptune as the Earth moves 1 year. And so it just takes a little bit longer than 1 year. The outer planets that move more slowly, the synodic period gets closer and closer to 1 year. So there you have it, the graphical method of finding the synodic period just by trial and error, guessing days and calculating positions around the circle. or with the official formula, make sure you're using years for the value for P, and you'll come up with years for the value of the synodic period, and you can convert that to months or days as you wish. So ask your instructor if you have more questions on this, but there is a difference between sidereal and synodic periods. Sidereal, the time for one orbit with respect to the stars. The synodic period, the time until we get the same configuration between the sun and the planets as viewed from Earth.